Hello, everyone, and welcome to our lecture on principles of motion and stability. And with this lecture, what I like to do first off is play a bit of a video because we're going to be speaking a little bit more to the physics and the describing movement and motion. And so part of this is going to be really useful when you go to do your first assignment. But it's also just a good starting point for all of us to have some common language in trying to describe what we see when we're talking about motor capacity. And so, again, I like to start with this really fun video of some X game athletes doing their respective sports. And it's just so impressive when we look at Tony Hawk or Shaun White or someone who performs these absolutely amazing technical elements in their respective sports, and they're all subject to the same physical demands of the world. So what do I mean by that? Well, for example, it's always hard seeing the falls, right? Head injuries in particular, whenever I see their heads hit the ground, it's just gives me a cringy feeling. But like I was saying, so whenever we see these athletes perform their elements, they're restricted and bound to the same physical properties of the world all across every athlete, every one of these sports. And a great example is gravity. Right? They're called the gravity games for a reason. And so these athletes have learned how to master the forces that are applied to them and in this world, and therefore achieve some pretty wild things. So today, we're going to go through a few different concepts, one of which is Newton's laws. So we get a better language and understanding of how they do that. So principles of motion and stability, they act on all movers, like I was saying. As movers become more proficient at skills, they often use these principles to their advantages. So what does that mean? Well, it just means, again, there's a physical world that's applied to all of us, and the way we become more and more proficient at moving, say, for example, in sport, is to utilize that to our advantage, to be as efficient as we can. And that's really what we're talking about when we're applying the mechanical aspects or the biomechanical aspects of sport and moving, is how can we make our movements the most efficient that we can, the most effective that we can, based off of these principles that apply to all movers. Okay. So learning to move, it's interesting. Whenever learners start, the efficiency of a moving body isn't quite there. So we can think of that when we're starting to learn a new movement or skill in a sport. But again, walking is a really good example of that. We can see we have our little mover here just learning how to walk and stand, and really there's a number of things, and we spoke about this last day, restricting and applying to this kiddo's capacity to move around. Okay, and one of them, again, the other day we spoke about different constraints. So this individual's constraints is changing every single day, and in such a large manner, right? Toddlers grow so quickly. So every single day, they're having to adapt and change their approach to how they move, right? That dynamic composition of how movement occurs needs to be refined and retooled every single day. So figuring out how to move most efficiently is a big deal. And in particular when, for example, you might move really efficiently on all fours. So maybe as a crawler, this toddler moves really efficiently. So there's actually less motivation for this kiddo to start learning how to walk. But eventually, kids want to be able to use their hands. They see people move around fairly quick on 2 feet, and that really encourages and motivates them to start learning how to walk. Just amazing. So crazy. So again, using a task constraint to try to get this kiddo to learn how to move and walk on 2 feet. That's great. So what happens when we take away some of those fundamental movements that occur and act on a mover? So what do I mean by that? Well, at the start of the lecture, I mentioned gravity, right? That affects all of us all the time. It's just a physical property that's there. But just as a little thought experiment, I want you to think about this for a moment and pause it and give yourself at least 30 seconds, maybe a minute to think about this. But does changing the physics experienced by all movers change the movements that are encouraged for the mover to do? So what do I mean by that? Well, let's take this for consideration for a thought experiment. And this might be a little abstract, but if we put a baby in space, never been on planet Earth, never been exposed to gravity on Earth, what does that look like for that mover? Would this baby ever learn to walk? There's no gravity. There's no encouragement to have it walk. You can consider what sort of movements would it become really good at. And so if you've ever seen people floating around a space station, there isn't a lot of walking at this point in time based off the design of space stations. But what does happen is you see them propel themselves around by pushing and pulling off of objects, right? That's how you generate enough force or a direction of your force to be able to move your body. So I would almost argue that if a baby had never been on Earth and never been exposed to gravity, what it would probably do is learn to use its feet and legs more often to help propel itself through a space station corridor. So for example, it would probably mimic a lot of the pulling and pushing that most astronauts do with their hands, just with their feet. And so again, I just want to have you consider that all these forces and actions that occur on us, but in particular people or toddlers that are learning to move new, is this environmental constraint on them of these physical elements of the world. Okay, things that are constant, the physics of the world we're in. Okay, we can kind of change that thought experiment a little bit. If children or babies were born and grew up on, say, a planet that had less gravity, so for example the moon, it's 1/6 the gravity of Earth, what would that be like? Would they develop the same desires to want to walk bipedally? Well, maybe, but they might be really good at bounding relative to human walkers. So for example, again on the moon, when you see people walk on the surface of the moon, if you see videos of that, you notice that there's a little bit of a bounding, and that's because each application of force tends to translate not as good. Or again, maybe we'll find, if and when there's a colony on Mars, maybe we'll find, if children are born there, that what ends up happening is they develop a new form of locomotion that's best fitted or most adaptive for 1/6 of gravity. Who knows what that is, right? Okay, fun speculation. And again, this whole thought experiment and activity is to try to get you to think about how the physical or the environmental constraints act on us as movers. Okay, so to be a bit more explicit here and say what we're looking at and show you in the diagram of Newell's model, we're really looking at the structural, so the physical components of our bodies and how they interact with environmental constraints. Okay, and to do so, we need to consider some biology, so how we're built, but also the physics of the world. This, if you're not sure what that photo is, it's a picture. There's never a photo. There's even speculation as to whether this actually happened. But, to clarify even a bit farther. So there is speculation, or the story goes, that Newton, sitting underneath an apple tree, had an apple fall, hit him on his head, and then he decided to write, mathematically explore, describe, and give us the law of gravity, more or less, and the groundwork for physics. It actually happened really differently. It was a bet between two other scientists, that the way planets orbited around the sun was elliptical or circular. So they're having this debate and this argument about it. And this is just an elliptical, kind of like an oval circle, right? So that's what this one gentleman was saying. And back in the day, they used to have like coffee shops and coffee houses were more places for people of academia to go, and it was kind of like a upper bourgeoisie sort of thing to do. And it was definitely the world of academia was a very a privileged one, in the sense that it was, if you were rich and had money, you would become an academic as a hobby. Okay, so anyway, that was a little bit of a background. I just think it's so wild and kind of bizarre to think about that the basis of physics that we know about today is based off of a bet that a couple of academics made in a coffee shop. So they make this bet. The one biologist's name was Hooke, and he ended up contacting Newton, who was at Cambridge, and was like, hey, or it might have been Oxford, sorry. But he's like, hey, Newton, you're a great mathematician. Can you prove mathematically that the planets go around the sun in an elliptical shape? And he's like, oh yeah, no, I can totally do that. I just had the calculations worked out here, but I've misplaced them. Let me redo them for you. And so, like, at that point in time, saying you knew mathematically that the planets rotated around the sun in an elliptical fashion, but you like lost the answer, was like saying, oh yeah, I got the cure for cancer here somewhere, I've just like lost it. So anyway, he ends up stowing away into his office and writing something called the Principia, which is essentially what we know as Newton's laws, and they're in 3 big chapters, but we aren't going to go into in that sort of depth. But just a fun story, something kind of interesting to know. But again, the foundation of physics that we know, Newton's laws, especially when we're looking at motion and how they apply. Okay? So the goal, again, ultimately, if you keep in mind, is how do people move to learn and perform movement efficiently? Okay? So the first law has to do with inertia, the second law, force, and the third law is that of action and reaction. Okay. So we'll go through each of those. So the first one, Newton's first law, an object at rest stays in rest, an object in motion stays at motion until acted upon by an external force. Now that sounds kind of funny. It might seem a little weird. It sounds like almost like you're saying if I throw a ball across a field, that it, according to this law, it should just stay in motion forever. But ultimately, and again, we'll explore this a bit more, is there's things like air friction and other forces like gravity that apply to this ball that stop it from just continuing on forever. So that's the unless acted upon by an external force component. Okay. So this is the law of inertia, first law. So to move an object, we need to apply a force. This makes sense. So if a soccer ball was at rest, it will stay at rest unless acted on by an external force. And here we have our star athlete, soccer player or football player, if you will, European football, coming up to kick the ball. So they're going to apply a force, right? And to change a direction, you need to apply a force as well. So if 2 athletes are running straight down a field or performing 2 different drills, one just runs straight forward and the other zigzags or goes around cones in a zigzag fashion, every time that one player has to change directions, they apply a force. Okay, the other one's just worrying about running forward. Okay. And then if there's no external forces, the object will continue infinitely. So let's go to a bizarre world again, or let's maybe just go back to space. And if you were to kick a ball in space, because there is no gravity, so we're going to pretend we're away from planets, so there's no gravity and no air, there's nothing to slow it down. So the ball would just keep going forever. Okay, and you see lots of there's been a few movies over the last 5-10 years or whatever, in particular, that have focused on what happens if you, say, get ejected and unclipped from your spacecraft. You just kind of continue forever. Okay. So that's Newton's first law of inertia. And another way we can kind of look at that is how that's applied to moving. So if I go to throw something, and this is, if you know cricket, or if you live in other parts of the world, you know, this is one of the most famous people you've probably never heard of if you've grown up and lived in North America your whole life. So Virat, he a very star cricket player. So the extent here that we'll need to know for how inertia helps or detracts from moving and applying it to motion is if we're thinking about getting an arm moving. So inertia, the ball wants to stay at rest and our arm wants to stay at rest. But the reason in, say, cricket throws or baseball pitches where we bring the ball close to our bodies before we start throwing is it's easier to overcome the inertia, so the desire for our arm and the ball to stay at rest, if it's close to our body. The farther the way it is from our body before we go to do the throw, the greater inertia that it has, okay? So this is just one example how intuitively we overcome the law of inertia without even really realizing it when we go to move, okay? All right. So that was the first law of inertia. Again, things at rest want to stay at rest. Things that are moving want to stay moving unless acted upon by an external force. Newton's second law says the acceleration of a person or object is proportional. So again, it's the same, proportional. If one increases, it'll increase. Proportional to the force applied to it, and inversely proportionate. So oppositely proportionate to its mass. So another way of saying this is the more massive something is, and mass is kind of like weight, it's a little different. So the more mass that something has, so the more atoms in it, the more matter it has in it, the less acceleration it's going to experience based off of a force applied to it. Okay, so how does that work? Well, you know, another way of saying that whole thing is force equals mass times acceleration. So if you look at this equation, and it looks mathy, but it's just a description of a relationship. So if the mass gets increased, the acceleration is going to come down. Because when you multiply them together, the product is the force. So another way of looking at that is if I apply 10 units of force, and it's a force is called newtons, but if I apply 10 newtons of force, regardless of the relationship between these two, it's always going to equal that 10 newtons of force to get something moving. So either we add something to become heavier and its acceleration will go down based off the 10 newtons, or the opposite. If something becomes lighter, I can accelerate it faster for that same 10 newtons of force. Okay? Go ahead and rewind that. Listen to it a couple of times if you need to. But ultimately, again, yeah, that just shows the relationship of the variables. So for a given object, because usually things don't change mass, typically, unless you're talking about a shopping cart or something like that. But if you're talking about something like shot put here, so we have our shot putter, and she's about to apply a force to this object. Now, again, the mass won't change, and we want to maximally increase the acceleration. So in this instance, our athlete is trying to apply as much force as possible to the shot put to get it to fly. So if we made the shot put really, really heavy, at the maximum amount of force that our athlete applied, it would just have less acceleration. So that's all it's saying. And that's how Newton's second law works. If you're having troubles picturing that in your head, here's a good example. So this force, the arrow represents the amount of force being applied. So a longer arrow would be more force. But because they're the same length, or we have our basketball player applying the same force, But you notice on this instance, and it makes sense when they're passing the basketball, huge amount of acceleration. Here, less so. Okay, so that's the second law. Again, there's one more picture showing the same thing. Again, if our person's maximally applying force, the car is going to move faster than the giant heavy tractor, right? Okay. Yeah, and I do like to mention work in here. You don't have to fully kind of understand, but it's just different than force. Some people say I put a lot of work into something. Well, yes and no. So work, just to make sure you don't use that term incorrectly when you're talking about forces applied, is the force times the distance. So a good way to think of this is a baseball player, let's say, putting the maximum amount of force in a throw won't change between two conditions. But in one condition, they step really large off the pitcher's mound. And another one, they step a short way. So if the force remains the same in those two instances, the time that the pitcher stepped the farthest is going to be the most amount of work done, okay? And that's ultimately because you multiply the distance by the force, and that gives us our work, okay? So to say someone did a lot of work is to say they applied a lot of force, but also over a great distance, right? You're talking about those two things, okay? Yes, so again, it's just for the same amount of mass, adding more force would increase the acceleration or make it easier, okay? Don't worry too much about the slide. I probably meant to take this out. Okay, so Newton's third law, here we are, third law of motion. This can be a little tricky. This can get a little confusing at times, but really it explains why things move when we apply to force to it, okay? So for every action, there's an equal and opposite reaction. Now intuitively, and I'm not a huge fan of this definition, but intuitively when you hear this, I know when I first heard this and understood it, it sounds like if I push on this hand pushes here, and nothing should move, right? If there's always equal and opposite reactions between everything, why do things move, right? It doesn't make sense. Well, one of the easiest examples to kind of look at and imagine is whenever you're talking about opposite and equal reactions, it's important to think of the systems. So define where these forces are acting, and then it becomes a bit more clear. So when we have our swimmer pushing off the wall here, yes, we see that. So there's that push happening. Our swimmer's pushing, the way I'm looking at it, pushing off the wall this way. Here's the wall. So the girl, the woman, pushes off the wall in that direction, but she moves that way. Now, why is she moving? Well, it's because of that equal and opposite reaction that she just applied to the wall. The only difference is the wall is so massive that the force applied to it doesn't cause it to accelerate at all. So instead, our swimmer experiences all the acceleration because she has less mass. So again, here's our swimmer, there's the wall it's pushing off, feet on the wall. So the feet pushing on the wall is this force. But the equal and opposite reaction, so the wall pushing back onto our swimmer's feet, is actually what moves our swimmer and the direction of the acceleration. So let's just suppose for a moment that our swimmer pushed off the wall and the force that she applied was so great it overcame the mass of the wall, right? So force equals mass times acceleration. Well, then the wall would start to accelerate and she would stay in place. Okay, but usually that's not the case. And you can think of middle instances where two things push off of each other, one moves farther than the other, right? And again, typically that has to do with where both of the forces are and how much each situation has. Let's take another look at that, okay? So another example would be with football players tackling with equal force. So what I mean, they have equal mass, equal acceleration, and they come into a collision. The collide, both apply equal and opposite reaction forces to one another, and neither of them move anymore. So let's take a look here. What happened when this purple football player here clearly overcame this player here? Well, the mass and acceleration, or the force, had a greater force than our other player here. Okay, and that's essentially it. So even though the collision that the purple player put onto the white and red player, they still experienced that force back. They just were met with less mass and acceleration, so they kept going in that direction. Okay, so there's still an equal and opposite reaction that happened, is just greater than what it was being applied to. Okay, so that's Newton's 3 laws. What's the consequences on human motion? Again, if you remember back to the start of the lecture, we're trying to explain how these forces, when applied to a mover, especially a mover trying to learn and adapt to all the forces applied to them, and the changing and dynamic approach here, ecological approach to movement. So Newell's model, so the individual, the environment, and the task. So we know these typically always stay the same. They're constantly applied. So when you're trying to learn in that environment, if there's ineffective and poor movement or injury, that's usually because there was some sort of poorly executed movement by the individual that didn't utilize the forces or the physical world around us very efficiently, effectively, or safely. Okay, and I have this GIF playing here where, if you notice the lack of efficiency in how our kiddos learning to move, the reason for that is because of these forces. So yeah, there's gravity applied, and through that they're needing to balance. But what's happening is there's this trade-off between how quick are kiddos moving or not moving, and and trying to maintain as much balance and stability as possible. And they're both a little different. We'll take a look at the differentiating the two in a moment. But if you can just, based off of your understanding of balance and in particular stability, look at how our toddler's walking. Okay, so when we know that they're walking, it's not necessarily like we would walk, which is very anterior, posterior, or forwards and backwards. If you notice, the legs kind of get lifted up, so it kind of like lifting high knees in front of them, and not only that, but it's a little wide, right? And obviously not moving across the room that quickly. Okay, and so this is where we're seeing how, based off of the forces in the world, the environmental forces, in order to be able to try to achieve this new motor skill, we have our learner moving inefficiently. But the point of that inefficiency is to increase stability. And regardless of whether you're a toddler or an adult trying to learn a new motor skill, you will see this occur. There is a trade-off for speed of the motor skill for stability. Okay, so stability, speed, trade-off. And again, yeah, now looking at this movement or the motor skill of walking for a new walker, you can see all the adaptations or the movement arising between the individual and environmental constraints here in the task to try to keep that balance, try to keep that stability with that nice high knees and nice wide stepping. Okay. So what is the difference between stability and balance? I kind of alluded to it. Well, you can perform something that's not statically balanced or not perfectly balanced. And a good example of that is, if we look at Sasha Cohen, was a former U.S. world level figure skater. Now you could look at this position and you can say, yeah, she's balanced, dynamically so she's having to balance quite a bit, but she's balanced. She's not falling over. And very similar with our sumo wrestlers here, they're both balanced. Okay. Now the and they're more statically or not moving balance, right? Now the difference here between the two is stability. So stability is the capacity to resist movement, or external movement in particular. But so if we look at Sasha here, would not be very stable in the sense that if one of us were to come up and just give a little push, she'd probably fall over relatively easy. Now, don't be fooled. She's very stable there, more stable than we might imagine, but just objectively, she looks quite unstable relative to our sumo wrestlers here. So very wide, low center of gravities. Those 2 points typically mean a lot of stability. Okay, so you can notice too, if we want to pop back to our walker, how when they're trying to stabilize themselves, they'll actually bend their knees and get a little lower, right there, right? So just trying to catch themselves. So low center of gravity helps, or center of mass, sorry, helps balance, or sorry, helps get stability. Balance, again, can be stable, dynamic, or static. And if we think about this too, when we run, our bodies are forward a little bit, and our center of mass is just in front of where we're going, typically, for some runners that are, say, moving very quickly, sprinters in particular. So is that a balanced position? No. If they stopped applying the appropriate forces, they'd fall over. So really, at the end of the day, regardless of who the mover is, in order to execute a skill, you oftentimes need to be in an unbalanced position, but that doesn't mean you necessarily lack stability, and vice versa. Okay, so again, just trying to differentiate those two terms in your minds. So right now, again, on your own, I kind of gave you examples as we went through the lecture as best I could, but I want you to try to come up and write 3 different examples as far as a sport of maybe your choice, or maybe multiple sports, of how to apply Newton's 3 laws. So inertia, so something wanting to stay at rest if it's at rest, stay in motion if it's in motion. Newton's second law, which is force equals mass times acceleration, or another way of saying that is force is inversely proportionate to mass. So the heavier something is, the more force you need. And then equal and opposite reactions, right? So if one force is applied, where is the other force, reaction force being applied, and how does that work? Okay, so go ahead, again, pause the video for a minute or so, give yourself a timer, and work through those 3, okay? Okay. I'm going to assume that you had done that. Yeah, and again, if you want, again, for study purposes or whatever, feel free to ask some peers, drop in for some office hours, ask me questions, whatever the case is, if you want some clarification on if your examples were good examples. Okay. So bringing it all together, physics is a constraint that acts on all movers, so it's an environmental constraint. Structural constraints, which are ourselves as individuals, often unify human movement in different points in development. So what does that mean? Well, we spoke about how when we're just learning to walk, for example, or we need to lift high knees. And a lot of the times it's because we lack a lot of stability and balance. One thing I didn't mention at that point in time is our heads are proportionately way larger than our torsos and limbs. So we're actually quite top heavy. So again, that's a unifying thing for most humans. So those structural constraints, we'll see that in development. And our next unit in particular really covers this point. And then last but not least, together those 2 points say that the task constraint, so whatever we're trying to do, can be generally predicted, idealized in a typical, most efficient manner. So again, getting back to like the biomechanics or the mechanical application of how we move, when we're talking about efficiency, effectiveness, and safety in sport, those 3 things really come down to the biomechanics of how we move, okay? And that, because the physics always apply to everyone the same, more or less, as far as like gravity is always the same force. Mass times acceleration is a force. Forces happen in equal and opposite manners. So because these are all the same, it's fairly confines how certain movements can be done. Ultimately, at the end of the day, as you know from Newell's and the dynamic systems approach to movement, or theory of approach, is the individual obviously is affected by the environmental constraints of physics or physical world differently, because everybody's body is different. But the fact that there's some unifying or universality, if you remember that term from last lecture, to the human body, we all have, I shouldn't say we all, many of us performing able-bodied sports have arms and legs. So there's a unifying factor there where we can say to some degree of correctness that these physical forces that are applied to us need to occur in a certain way to be effective. Okay, great. Okay, so that's up for today. Just recall that we have our unit quiz coming up, at which case after that we'll get into our next unit, which is FMS, and that's when your first assignment will be given to you, and details regarding that. Okay? All right. Email me with any questions that you have, and happy studying.